Good afternoon. Today we're going to do a project, and to me it's one I've actually been working on for about 10 months now. I haven't had time to complete it, and within the last few weeks here I finally got around to wrapping it up and getting it completed, and I've taken some of it apart right now just to kind of show you the ending of assembly and so forth. But it's a very cool I guess you call them novelty clock. The way the hands work and the gearing inside is, in my opinion, it's engineering genius. And I found this on Thingiverse while I was looking for something else, or maybe it was one of those early morning things, and I was just scrolling through all the cool stuff that's on there, stumbled across it and knew I had to make it. Now, it was originally designed and powered with what I believe was Arduino, and I didn't want to go down that road. That takes the fun out of it for me. So I thought, well, I'll just adjust a few things and we'll make it suitable for those of us in the Raspberry Pi Pico world. Let's take a look at it here on their website, or on the Thingiverse website. Really, the bulk of the information you need for printing it and the mechanical assembly you're going to get from their website. But here's the device when it's completed. They got a video on here, links to other clocks that are similar in design, which you'll have to refer to for more assembly tips and wiring and things of that nature. But this person, I'm going to butcher the name. I tried to pronounce it earlier and I keep goofing it up, but I think it's Shiura. I'm sorry. Hey, great job on the design of this thing. It's just cool as all get out. And I hope you keep creating such wonderful things. But it's very well documented and so forth. And all I needed to really do is create a different base and a bottom for the base where the electronics go. And I'll have step files and STL files that you'll be able to download from our website like we always do with most of our videos, so that you have what you need to do the project. So anyhow, you'll go to this. I'll provide a link for this in the description below. You'll need a 3D printer, such as that guy over here. You don't need one quite that big. I believe it'll be suitable for most sizes. And then you're going to purchase a couple of things. Oops, I didn't really want to do that. That was a jerk there. You'll need to pick up these stepper motors and this stepper driver. This isn't my first choice, but I didn't want to go through and redesign gearing and so forth. And in truth, it works quite seemingly nice. So I'm perfectly happy with it. In fact, the kit comes with 5 motors, 5 drivers, and I'm down to having, after the clock, I think I've got 1 pair left. So I've been using them on other projects as well. It's $11.99, so per piece unit's pretty inexpensive. But that's how the clock is powered. It's driven by a stepper motor. Therefore, you don't hear that constant click, click, click of a pendulum clock, which can drive people nuts too. You'll see I have a clock here. This one I built, I guess, maybe 20 years ago, give or take. It's a wind-up clock. It's really beautiful, makes beautiful chime sounds, the whole 9 yards. I just can't stand listening to the thing tick and tock. So it's a decorative piece now. You'll also want to pick up, I found this one, you'll see on my version. I'll show that here on this camera. I use the 3-button variety, which you see here, but finding them again is getting more and more difficult, and I don't understand why, but you'll want to have a simple button system, and this is, to me, one of the most simple and very easy to work with. This is $2.98, but it's looking like it's about a 3-week lead time on them out of Amazon. If you want to go with the 4-1, I think there's shorter versions of them that you could use as well. But those are probably the most difficult items you need to get: the stepper motor, the driver. Of course, you're going to need a Pico. And you'll see here that this particular Pico, I soldered on the headers upside down to traditional. They point up instead of down, and that just makes wiring a lot easier, and we'll get into that a little bit later. Writing the code for it, very simple. We're just sequencing this stepper driver in a very simple way. And we'll go through the code again after we get through the assembly explanation. So what I've done, I've already gone through, filmed the section for the assembly of the clock, and I'll narrate over it, and that'll be fast forwarded so that you don't have to sit through 30 minutes of me droning on about the assembly, because it's really not that difficult. Print your parts and carefully remove the bumps and burrs. Dry fit all your parts and make sure everything moves smooth with no binding. That's going to be key to the success of this clock working. Make sure you have screws for the parts that are screwed together. They're very tiny. You'll have to maybe get some off of Amazon. I recommend using the lithium grease. That's the grease that I found that there's claims that it does not affect PLA plastic. And you want to apply that liberally to all the moving parts. And the purpose of the grease is not only lubrication, but also to add internal friction so that the movement of the hands isn't as jerky. You'll go ahead, install the stepper motor now, and then press the gear onto the motor shaft. And you just do that with finger pressure. You want to test fit that before assembly. Assemble the two rings together, and then clean up the grease as you're going along in this process. You'll screw on the back of the minute hand, screw on the hour hand, and you may need a little pad. A piece of felt works good between the back of the hour hand and the front of the minute hand. It just adds a little friction again so it doesn't act so jerky sometimes. You'll install the Pico in the base, again with small screws, and then you'll do the same for the stepper driver board. I would recommend that you sand the back of the base smooth to help with adhesion of the membrane buttons, the keypad device. Then you can go through, connect the wires per the schematic. I'll be providing a fritzing diagram. I made jumper wires, but you can solder or just use standard jumper wires, whatever works for you in projects like this. And then we're going to attach the bottom of the clock to the rest of the clock. And that is part of the original kit. And that gets screwed on. From that point on, because I'm not 100% sure if this thing is perfect or it needs to be worked on, I'm using double-faced tape to hold our base, the one that holds our electronics, onto the bottom of the clock. And then that way I can take things apart as needed. And then once I'm sure everything is good, I'll super glue it together. And then there's the outer ring on the clock that kind of is like the stylized numbers on the face of the clock. And that can just be clipped on and then held in place with temporarily with some glue or with some tape, and then super glue to permanently bond it once you're sure the clock is working good. In truth, the assembly is quite simple. Most of the details are in the preparation of the 3D printed parts. You know how it comes off the printer. Sometimes you get little globs, little nibs, burrs, elephant's foot, all kinds of little things. Clean it up with a sharp knife and get it in as good a shape as you can make it. Regarding the grease, this is the type that I used. Obviously, any quality brand of white lithium grease will be fine. This just happened to be what I found quickly at an auto supply store, so that's what I picked up. Now, I probably got enough grease here to build about 50 of these clocks, but obviously white lithium is used in other applications as well. As far as putting the components inside this case, this is self-adhesive. Here you can see I've got a port there for the USB of the Pico, and that is also how we'll power it. I've been using it in testing with one of these devices and a USB-A to micro USB adapter cord, and it's been working perfectly good. I think the transformer cost me $3-4, and then the cable I just had laying around, but those are economical as well. But this was self-adhesive, and that's why I recommend sanding that flat so it bonds good. And then I made shorter jumpers, and of course, if you want, you can use this style of jumper as well, or even solder some of these wires onto the components. The stepper driver looks like this, out from underneath all the wires. And you'll hear me talk about a ULN 2803. This is a ULN 2003, I believe is the part number. So it's a buffer between the Pico and the stepper motor, and acts as a driver as well. We will be using the white connector here because that's what comes off the stepper motor. And then we're going to hook up to the power here, and then our outputs from the Pico would go along this bank here, as shown. The LEDs are really cool. For no purpose other than helping me show you how a stepper motor is phased when we're stepping through the various steps of rotation or micro steps of rotation. You'll see the LEDs blink, so that's kind of cool. We'll be doing that here in a moment. Now the rest of the assembly, this would be glued onto the bottom of the clock, or as I'm doing it with double-faced tape. One of my favorites right here. I usually have about 6 to 10 of these rolls around for various things that I work on, especially out on the CNC. But I'll be using that to adhere this to the base until I'm 100% sure the clock is mechanically sound. Once that's on, then the base, the 3D printed base, which is a part that I'll be providing the files for, locks in, friction fit. I've got areas where you can put screws in, and then I would recommend some little rubber feet for it as well, just to finish it up. If you got to use screws, that way when it's sitting on the rubber feet, it won't be resting on the screws, scratching a tabletop or some such. Now, because of the design of this, oh, and by the way, the buttons go toward the back of the clock. We can just take the USB cable and, of course, plug it in the back, like so. And literally right now, the clock is running. And here's the sequencing of the different phases of the stepper motor to make those tiny little steps. And this is a geared stepper motor, so it takes a lot of steps to get it to move one rotation. Now let's take a look at the code here real quick. We've got some commentary at the top, some links to where the items are. I'm going to try to make sure everything's in there for the purchase components. Of course, you'll have that in the links down below and other documentation as well. No Wi-Fi needed, 3-button memory. I did find the source for this now, so I'll remove that comment. Calculating the steps per second and time per step. Just follow along with this so you get an understanding of it. It requires several steps to get through it because of the gearing, how many steps per revolution of the motor, etc. I don't really want to get into the heavy details of controlling a stepper motor. That's definitely a big separate video all onto itself, controlling stepper motors. There's a number of ways to do it, and I'll be doing probably a couple of videos on that shortly. We're going to import our machine library and time. We're going to set up 4 outputs, 10, 11, 12, and 13 on the GPIO numbering. And those will be referenced of P1, P2, P3, P4 for the phases of how we index the stepper motor. And that also relates to those LEDs that are blinking right here. For the membrane switch, where you need 3 inputs, green, yellow, red are the buttons, so that's what I called them. And those are on pins 18, 19, 20. And I did set the pull-up resistor so that we're in a on state all the time. And then when you press the button, you drop it down to low signal or switching it to ground. Here's the instructions on how you would set the time on the clock once you've got it all powered up and running. And then here's the phase sequences of how we go through to smoothly index this stepper motor. And the one is showing which phase is on and which one is off. And that correlates, or which output is on and which output is off. And that correlates to how these LEDs are flashing as well. So we're actually going to be turning on these two, off those two. Then the next time, I'm going to turn on, off this one, leave this one on, and then so forth, going all the way through, and then it'll loop back around again. Up here, we're talking about how the speed of the clock is controlled, and this is the theoretical normal clock speed. And I didn't expect it to be spot on, so I'm also adding a little, we'll call it an offset here. I'm multiplying it based on my first test. I needed it to run about 1% longer between sleep statements to slow down the clock. It was running too fast. And then I did find out that it was needs to be slowed down. So I'm going to make another modification to that. And I'm going to keep these in here commented like so that I keep track of which way I'm adjusting. So now I'm just going to say need clock to slow down, clock to slow down. And to slow down the clock, we increase the time of the sleep. The longer it sleeps between steps, the slower the motor goes. And as I'm saying that, I just realized I need the clock to speed up, not slow down. I went too far on my last adjustment. So what I'm going to do is, and it wasn't much, it was a few minutes every day. So I'm going to go to about 0.085, just slowing it down ever so slightly with that factor. And this will be one that you'll adjust through trial and error to get your system to run on time. Then we've got this adjust speed. That's when we're adjusting the time. The hands move very rapidly. And then we're going to have a variable that'll keep track of which phase I'm on so I know which phase setting to go to next. And that has to do with the sequence of ons and off in this area. We got to handle, because the phase is in a counter, it'll roll over. When it gets to 9, I want it to become 1. And when it's less than 1, I want it to go back to 8. So it's essentially from 1 to 8, representing these 8 items here. Got some print statement to help with debugging as needed. And then this is the thing that's actually doing the work in this function for stepping. And if I want phase number 1, or if I'm on phase number 1, I would go through and do all of this. And then if I'm on phase number 2, I would set the ons this way and so forth. And then at the end of here, this is the sleep that we add, sleep, that speed amount, time.sleep.speed, and that will come from here, be passed into the function, and that's how we get the clock timing just right. We get down to here, we've got 2 variables, one to make the clock run forward clockwise, imagine that, and then one to make the clock run counterclockwise, or the rest of the world would say anti-clockwise. So that's just a 1 or a negative 1. Remember, if we're adjusting the clock, we may want to run it backwards. That's why that's included there, just for time adjustment. And then we go into an endless loop. This is a clock. It has to run forever. And then we're going to deal with the switches. If red and yellow are pressed, we will step counterclockwise, go backwards at fast speed. And now notice that this is if red is equal to 0. Remember, a button press is 0, and then not pressed is 1. Then green being pressed and yellow not pressed, we're going to make it fast forward as we hold in the green button. Down in this area, you'll notice that if red and yellow are both pressed, adjust time equals 0. That'll make sense in a minute here. For AT in range 56,320, the number of steps to make a full complete hour go by, we pass in step, counterclockwise adjust speed, sending in the adjust speed time. And that will make it run fast reverse for 1 full hour. It's daylight savings time, just that nice little thing to make it easy for us. And then the same thing with the green button and the yellow button. That'll make it go forward 56,320 steps or pulses, and then that's going clockwise at that adjust speed. Otherwise, we're just going to step clockwise at the normal speed. And so this just repeats and repeats and repeats forever, hopefully, at least while power's applied to it. So again, the speed is being passed into this function from down below here, and we're selecting which speed to send into it. Either it'll be normal speed or adjust speed if we're adjusting the time due to power outages or daylight savings time, etc. And that's kind of the whole program. There's really not a lot to it. A very important part is, notice it's called main, and that will be the way that the thing automatically starts running when it's powered on. So we just plug in the power supply and the clock starts running. So now what I'll do, I'm going to use some double-face tape, get this piece mounted back underneath the base, get the base put on here, and then we'll be right back after I get all that taken care of. And now the clock is fully assembled and running. Using that little transformer and a appropriate cable, and working along just fine. I got to set the time on it, and this is where I would explain to you how to do that. On the back, we got the 3 buttons, so if we hold in the yellow button and hit the green button, it'll advance forward 1 hour. And then likewise, if we hold in the yellow button and press the red one, it'll go backwards 1 hour. Now, you can also hold in either the red button to go backwards in fast motion, or hold in the green button to advance forward in high speed. And that's as fast as it'll go with the sequencing that we've got built into it, with that very short delay, the sleep cycle between steps. So once this gets stopped, I'll just show you what it'll look like. And then I'm going to show you one more trick we can do so we don't have to adjust so far on it. The other hand is actually friction drive. It's not mechanically bound to anything. So if we want to kind of scoot that along so that we can set the time a little more quickly, that's certainly well within our rights to do so. So we're at 12:57. So I believe that's 50. That'd be about 57 right there. And so that is almost 1 o'clock, so I can easily move the hour hand up like so. And so that's it for this project. Frankly, it was a lot of fun. I wish I was able to do it all in one continuous flow instead of spreading it out over 10 months or so. But I'm real happy with the look of it, real happy with the results of how it all came out. I know I got a little more tweaking to do to get the timing just right, but it's real simple to do with that multiplier factor. And from now on, it'll probably be there in a couple of videos that I'll be filming in the coming weeks. Thanks for watching. I hope you build one of these, and if you do, be sure to tell us about it in the comments below. See you in the next video.